This is the second lesson for 244, and it's another review lesson. This is covering the topic of hypothesis tests for one proportion. Hypothesis test is a process for testing claims about a larger population based off of a sample. Here's the process for a hypothesis test. State one, you have to state the null and alternative hypothesis. This is what this does. The null hypothesis, this typically represents the base kind of claim. Null meaning no change. So this would represent like no change in 1 year from next year. Alternative hypothesis, this is representing how we're sort of anticipating things to change. So something could be less, greater, or not equal to that same value. Second step of a hypothesis test is we determine the model and check assumptions. For today, we're going to be testing claims about proportions, so we're going to be using the same model from last time. To analyze sample probabilities, we use a normal model with an average or center of p and a standard deviation of square root pq over n. As always, there's 3 assumptions for using these sorts of models. Random, by that I mean there's little to no bias. Independence, one thing does not affect another. That's hard to check. The backup for that's the independence 10% rule. And finally, a large n. Large n means I anticipate n times p, 10 successes and 10 failures, n times q. So what I'm doing in this first step is I set up what I think roughly what I anticipate something to be fair and not fair. And in the second step, when I'm setting up this model, I believe the claim for now. So here's a picture to kind of help with how I visualize what's going on. When I create this distribution, in the middle of it, I'm going to have the value from the claim that they're telling me. Now, what I actually get from my data might be really close to the claim, so my data might show up here, in which situation I might think that maybe this is a fair picture. They tell me it's 50% and it's actually 50.2%, not that far off. Or maybe my picture looks something like this, where I have my claim in the center. Claim is always in the center. I'm assuming it's true. That's what I mean by when I say I assume the null hypothesis is true. I put it in the center. And let's suppose this time that my data is way out here. They told me I should have a 50% success rate, and I have a 90% success rate. That's considerably larger than I was anticipating. If it's this far away, I might think that it is not fair. And the way I'm going to judge if something is fair or not fair is based off of this distance away from the claim to the data. In particular, we can actually look at the size of this tail here. And I call this tail the p-value. The p-value is the likelihood of the sample data from the sample data, or more extreme, if I have the claim in the center. So a couple of things to keep in mind. In this situation where I have a really large shaded in region, the shaded in region is the p-value. If I have a p-value that's bigger than, let's just say 5%, in this situation, I might want to think of it as being potentially fair. Now, if I have a really, really small tail, if this thing is just way, way out there, p-value less than, let's say, 5%, I might tend to believe that it is not fair. I'm using 5% because it's matching up with that 2 standard deviations. My usual values happen 95% of the time. So kind of the opposite of that happen 95% of the time, unusual would be these 5%. So I'm saying if I have an unusual situation, I might think it's not fair. If I have a usual situation, well, maybe it's fair. So if my p-value is less than my alpha, I reject the null hypothesis. I'm in this not fair situation. I reject the null hypothesis. I have evidence of the alternative. If I have a large p-value, I fail to reject, and I just kind of stay in place there, and I do not have evidence of the alternative. The way that I remember this, if the p-value is low, the null must go. So if I have a small p-value, I reject the null hypothesis. And reminder when I'm writing out this null and alternative hypothesis, and I'm going to start this in example 1 already. I'm going to start the framework for it. My null and alternative hypothesis. My null hypothesis is always going to have an equal. And whatever symbol I have here is a claim about a population of interest. And if it's a population of interest, I'm going to use parameters instead of statistics when I'm writing down this number here, this symbol. So reminder of what those parameters are, I have mu. I'll use mu if I have a claim about an average. Sigma, I'll use sigma if I have a claim about a standard deviation. And p, this is my symbol if I have a claim about a percentage. So let's look at this problem and see which symbol I should be using. It says previously 80% of Comcast customers were satisfied with their service, and they want to test if they've improved. So looking at this, it seems like this is about percentages. So I'm going to use the symbol P there. The number that's the percentage that they give me there is 80%. So alternative hypothesis P, the number will always match up, the symbol will always match up. The only thing I have to change here is the symbol. In this case, they want to test if they've improved. Well, if Comcast has improved, instead of having 80% of customers that are happy, they would probably have more than that. So for my symbol, I would have greater than 80%. This represents improved. At least improved in this context. We'll see how improved is one of those words that sometimes it will tell us less, sometimes it will tell us more. So I've done the first step. I've determined my null and alternative hypothesis. Second step, I should check the assumptions. I'm going to ask that you do that on your own here. And model. Let's come up with the model. I'm testing about percentages, so I'm using this p-hat model. I'm going to be looking at sample percentages when I put them down on the curve. Suppose it is normally distributed. It'll have a center of p. It'll have a standard deviation of the square root of pq over n. Now, if I had the n, I would plug in the n here, but I just want to show you kind of roughly what the setup would look like for at least what I have so far. I would plug in p. P is 0.8 or 80%. I would plug in the q, 0.2, and I would plug in whatever my n is. So when it comes time to sort of draw this curve out, I would have whatever my value is, 0.80 as a claim in the center, and whatever this is, that's the amount I'm sort of adding and subtracting. So I'm going to be making up some values here. We're going to do this whole thing later on step by step, but I'm just kind of showing you the rough, broad strokes of what's going on here. So I'm going to use a made up p-value. Later on, we'll calculate where these sorts of things come from. I currently don't have enough information to come up with the p-value, but let's suppose that I have a p-value of 3% for this problem. So I'm going to draw that in on my curve here. So let's suppose they say it's 80%. I actually end up with a sample way up here. And when I shade this sample in, I end up getting a p-value or size of this tail of 3%. Made up number for now. Later on, we'll calculate it. So as a final step, after I've set up my claim in the center, I've come up with my model based off of that claim. That means I'm putting that claim in the center of my model. Third step, I compare my sample to my claim to find the size of the tail. The tail is called the p-value. I'm making it up this time. We'll calculate it later. Final step, I want to determine if this seems close to the center or not close to the center. In this case, this looks like it's pretty far away from the middle. I'm verifying this by the fact that 3% is smaller than 5%. So since my p-value is less than my cutoff for what I consider rare, and alpha is symbol for what I consider rare to be, since my p-value is low, my null must go. So since my p-value is low, I must reject the null hypothesis. If I reject the null hypothesis, I must be leaving it for something better. I don't just leave it and then I'm left in limbo. I only leave something when I have a safety net. So I reject the null hypothesis. I have evidence of the alternative. And I'm not just going to say I have evidence of HA. I have to write this in context so that way people know what this problem is really about. In this case, I have evidence Comcast has improved. So they used to have an 80% satisfaction rate. Now it's higher than 80%. If you're wondering, well, what would their current satisfaction rate be? Let's say I wanted to be 95% sure I knew what their current satisfaction rate looked like. Well, that would be an answer that would get answered using a confidence interval instead of with a hypothesis test. Okay, I'm going to do the same kind of setup here. I'm going to be skipping steps 2 and 3, and I just want to practice this writing down these hypotheses and this conclusion step. In a lot of ways, this is the most abstract part of the hypothesis test, so I really want to make sure I have that down before I start doing some concrete examples. I'm going to flip the page and do some more with you here. Last year, the average length of a flight from San Francisco to Portland was 90 minutes. Okay, I see a couple of things. I see average. I'm remembering that I always have to use one of 3 parameters, mu, sigma, or p. I'm using mu when the problem is about average. I'm using sigma when it's about standard deviation or how something varies. And I'm using p when the thing's about a percent. They hope they've improved. If they've improved the flight, that means they're more efficient. If they're more efficient, that must mean it takes them less time. So I'm just going to do first step. And then I'm going to do the 4th step. And when I do this 4th step here for the conclusion, I'm going to have a made up p-value, at least for now, so we can practice that skill a bit. So my made up p-value in this case is 0.049. If you're following along using this video instead of going through an interactive class setup, I'd ask that you would pause and try this out on your own first before we go through it together. I'm going to start going through the problem. This is a problem about averages, so I'm going to use the symbol mu. So for the null hypothesis always equals, the number in this problem is 90, so I have 90 minutes here. And my symbol is mu. Just a little matchy-matchy, so mu, 90. Only thing I have to change is this symbol. And in this case, if they're more efficient, it would mean it takes them less time. So in this case, improved meant less. In the problem before, improved meant more. So I have to be really careful with language as I'm going through these problems. It tells me how to set them up. So if I'm looking at this problem, and I just wanted like a mental picture of what's going on, my center of the claim is 90 minutes. Just as a note, whatever direction this alternative hypothesis points is the direction I would shade. This says less, so when I was drawing my picture and I was actually doing the problem, which I'll do these later, it would be shaded to the left. And I have a made-up p-value for this tail of 4.9%. All right, I'm going to do the conclusion now. I'm noticing that my p-value 4.9% is lower or smaller than 5%. If my p-value is low, the null must go. If I am rejecting the null hypothesis, I'm leaving this for something better. I must have evidence of this second sentence. And I'm going to write that in context. I have evidence the average flight length is less than 90 minutes. You might want to be more specific and say the average delta flight length from San Francisco to Portland. I'm just writing like a bare minimum sentence here. It's definitely a good idea to go a bit further. Let's look at another one. I want to test if a coin is fair. Again, I'm just going to practice kind of the step 1 and step 4 of this. I'm going to have a made up p-value here. My made up p-value this time is 0.051. If you ask me where this number came from for my made up p-value, I would draw a picture of a hat and an arrow coming out of this hat. I'm just making this number up. I would like you to try to come up with the null and alternative hypothesis for testing a coin for fairness. And then what would your conclusion be? Do you think you would reject? Would you fail to reject? What would that mean in the context of testing to see if a coin is fair? If you're doing this at home, think about taking a minute to pause the video and try it on your own. Let's try it out together. I want to test if a coin is fair. Now, I know when I flip a fair coin, I usually get heads 50% of the time and tails 50% of the time. So even though it didn't say average, standard deviation, or percentage, in my head, I know that for fair coins, I get heads 50% of the time. So for all the alternative here, it should still be P, it should still be 50. There are a couple ways that a coin could be unfair. If I got heads 0% of the time, this means that I got nothing but tails, and that would be an unfair situation. Let's take it to the other extreme. Let's suppose you get heads 100% of the time. That means you've gotten nothing but heads for your coin flip. That would also be unfair. So in this situation, having too low of a number and too high of a number would both be unfair. So if I'm thinking about what the picture would look like here, I'm worried about values being too small, but I'm also worried about values being too large. I'm testing for different than 50%. When I'm drawing the picture for a two-tailed test, you're always going to see something like this, representing both less and more for does not equals. Now my p-value is made up, okay for now. Let's try to determine if this is large or small, and if we should reject or fail to reject. I'm looking at 5.1. I'm realizing 5.1 is bigger than 5. So I would say my p-value is bigger than or equal to my significance level. That's a fancy name for this thing, significance level. If my p-value is large, I fail to reject the null hypothesis. I wanted to be able to say that the coin was unfair, but unfortunately, I'm stuck at that null hypothesis. In other words, I do not have evidence of the alternative. I don't have evidence of the coin being unfair. Otherwise, I would say the coin is unfair. So I do not have evidence that the coin is not fair. Just a follow-up note here. A lack of evidence for one thing does not provide evidence for another thing. For example, if I flip a coin and get heads, that's not enough evidence for me to say the coin is fair. That's not enough evidence for me to say the coin is not fair. Sometimes I don't have enough evidence to say anything. So if you're reading this sentence and you're thinking, well, this proves its fairness, don't think that. You can never accept this null hypothesis. You can only lack evidence of something better for now. All right, one more of these things. A ruler manufacturer states that their measuring sticks vary, so I'm thinking standard deviation here, by 0.01 inches. You think they actually vary less, okay? I'd like you to take a moment and see if you could come up with an alternative hypothesis. For the fourth step, again, I'm making up a p-value here. Let's suppose that made up p-value is 0.999. If you're doing this at home, take a minute, pause, see if you can figure it out on your own. Okay, let's give it a go. I'm working with standard deviation. My symbol for standard deviation is sigma. It looks like Charlie Brown. The value that they're giving me is 0.01 inches, so I'm writing that down as the number. I always have equals for the null hypothesis. For the alternative, I think it varies less. If I was drawing this picture out, in the center of my curve, I might have 0.01. My actual value's over here, and hold up, my p-value, dang, that's really large. So my p-value in this case is saying I've shaded in almost the entire curve. That's a crazy large p-value. If I have a p-value bigger than 5%, my significance level, I fail to reject the null hypothesis. In this case, I would say I do not have evidence of this alternative statement. I want to be able to say that, but I can't. I'm kind of stuck up here. I do not have evidence that the measuring sticks vary less than 0.01 inches. Just as a note, the reason why I don't have evidence that it varies less than that is if you think about this little tail here, that would be tiny if I was testing in the opposite direction. In fact, if my alternative hypothesis was testing for them varying more than 0.01 inches, I would end up with a p-value of 0.001. In this case, I would reject the null hypothesis and I would have evidence that it is more than 0.01 inches. The reason why I don't have evidence for less is because I actually have evidence for more. This is why I should never accept that null hypothesis. I don't want to say it's equal to 0.01 inches because there's a chance that it could actually be considerably higher than that, or just a completely different number altogether. I have to be careful as I'm going through things. This is sort of what it looks like for the first step and last step. I've really been leaving off that second and third step. So let's look at one of these things from start to finish. I'm going to turn the page and I'm going to look at example 5. So suppose that according to Time magazine, 33% of all cars sold in the US are SUVs. After some investigation, it appears that the actual value is less than that. Suppose that a simple random sample of 500 vehicles shows that they are 145 are SUVs. Let's test the claim. I have a 4-step process for going through this. So I'm just going to kind of make a template for it. First step, I'm going to have that null and alternative hypothesis. This feels like it's about percentages. It might be about P. Second step, I'm going to have model, and I should check assumptions. Third step, I should calculate the p-value. And this is low on the page, but fourth step, conclusion. Let's start at the beginning and work our way down. So hypotheses, I'm going to have 2. This is about percentages, so I'm using P. For the rest of the lesson today, I'm looking at hypothesis tests for one proportion. So this means all of my null hypothesis for this lesson will look like P equals number, one proportion in that setup there. And it's claimed that it's 33%. Well, we think the actual percentage that are SUVs is less, so I will have less than 33%. Again, the symbol in the alternative hypothesis, this determines which way I'm going to shade. So when the time comes later in the problem, I'm going to have this thing shaded to the left. Reminder when you're using the normal table, if it's shaded to the left, you're going to use the value inside of your table. If this happened to be shaded to the right, we would do 1 minus the table value. All right, so when I'm finding the size of that little tail, and I'm thinking ahead a bit, I'm going to have a curve, and I know in the middle of the curve, I'm going to believe them for now, I'm going to have 33%. So let's find out what our center and standard deviation should be for this model, going back to the formula. I'm looking at percentages. I'm going to put sample percentages on this curve. It looks like a bell. It's the normal model. P, standard deviation root, PQ over M. I never plug anything in for P hat here. It is the name of the model. I never plug anything in for N. That stands for the normal distribution. For P, that's my center. I plug in the claim of 33%. In this first line, I said every time that P shows up, put in the number 33. P showed up here as well. Q is the opposite of P, or the complement. So if I have a 33% success rate, while 100 minus 33 is a 67% failure rate. And finally, my N. I'm looking at a sample of 500. So my lowercase n is 500. I'm going to type that standard deviation into a calculator here. And when I do that, I get 0.021. So on my curve, the center is 33%, and I'm adding and subtracting about 2%. So this would be like 35.1%. This would be like 30.9% or so, just a rough picture. If I'm checking my assumptions, first assumption is random. Looking at the problem statement, it says they've selected a random sample. So in this case, it says so. My second assumption is independence. One thing being an SUV should not affect another thing from being an SUV. It's not like you're driving down the highway in a car and all of a sudden your sports car turns into an SUV. They don't affect each other at all. So one vehicle does not affect another. If you're thinking, well, what about if I was in a neighborhood and everyone owned expensive sports cars or everyone had SUVs, then one person having something would affect another person having something. That might be true, but we're looking at less than 10% of all vehicles out there in the world, so it's highly unlikely that we're sampling two individuals that are affecting each other. So I can assume independence, even if I'm worried about some of those special niche cases. Finally, large N. 500 times 0.33 gives me a value of 165, which is bigger than 10. Now here's what this means. I am expecting for a sample of 500 to have about 165 of those things be SUVs. That means that everything else, the 67% of that, or the 335 other things in that sample of 500, must represent my failures, not SUVs. That's also bigger than 10. The reason why I need such a large sample here is this actually causes there to be 165 kind of blocks in one direction, 335 blocks in the other. Because if I graph these things, it's not actually smooth. The graphs for these things start out kind of like these binomial sort of shapes that are kind of jagged. But as I sample more and more, this will get smoothed out. It takes at least 10 successes and 10 failures in order for this to look smooth enough to say, even though it's jagged, it may as well look like this. Okay, hypotheses, my model, I'm expecting this, p-value. The p-value is the likelihood, and do you see how I'm setting this up? I'm going to read that definition that I had on that first page, and as I read it, I'm going to write it out. The p-value is the likelihood of my sample data. My sample data is my sample success rate, 145 out of 500. So I have the likelihood of my sample data. Next part of that definition says, or more extreme. So whatever symbol I have in the alternative hypothesis, that's the same symbol I have here. And it tells me which way to shade. So the p-value is the likelihood of the sample data or more extreme. In this case, my sample success rate is 29% if the null hypothesis is true. So I'm going to try to answer this question if I use this picture on the side. So I put down 29% here, and it says shade to the left, so I'm going to shade to the left. I have a normal distribution problem. The way that I do these is I draw my picture, done and done. I find my z-score, and then I look it up in the table. And as we mentioned before, if the thing is shaded to the left, then the area, your p-value, is just going to end up being that table value we get when we look this thing up. So let's find the z-score. Reminder, the z-score is your value minus the center divided by the standard deviation. In this case, my value is 29%. My value is always going to be my sample. So I'm taking my sample here as that first number. Minus the center is always going to be the null hypothesis claim, in this case 33%, divided by my standard deviation. I calculated that to be 2.1%. When I type this into a calculator, I get negative 1.90. Reminder of how this works. First two digits give you your row. Last number gives you your column in the table. So get out your normal table. I'll get mine out too. And inside of your normal table, go to the 1.9 row and the 0 column and see where those things meet up. So I want 1.9 for the row, 0 for the column, and I want to see where those meet up. This gives me a table value of 0.0287. So the size of my tail, that's my p-value, is 2.87%. So I'm practicing that final skill, the conclusion. This is pretty low because my p-value is smaller than 5%. And we're using 5% as our cutoff for now. We'll change it later. Because rare kind of depends on context. So missing 5% of basketball shots, not the end of the world. Misdiagnosing 5% of patients, probably a bigger deal. So 5% will be really, really context dependent. Long term, 5% is sort of my neutral kind of basketball, not the end of the world kind of number. So my p-value is low. My null must go. I'm going to reject the null hypothesis. Going back to my hypotheses, if I leave the null hypothesis, I must have evidence of something better. So in this case, I have evidence that, and the direction for this was reminder less, I can see it from the picture, that less than 33% of vehicles are these big SUVs that I see on the road sometimes. So this is what the thing looks like from start to finish. I state my hypotheses, I have my model, I compare the claim, which will always be in the center, to my data, and I see if it's close or not close. In this case, I have a really small p-value, I reject the null hypothesis, I have evidence that it is unfair. Unfair in this case means it's less than 33%. I want to look at another example of this, and I'm actually going to skip a little bit. I'm going to go forward to not page 4, but page 5. And I'm going to look at a two-tailed test now. Because after this, literally every single problem is identical in the sense that it's always the same 4 steps. I'm always doing hypotheses, model, p-value, and conclusion. So let's see how this problem is different, if it's different at all. So how would the previous problem, the one about the SUVs, change if we thought the actual value was different? Okay, I'm noticing the same numbers here though, 33%, 500, and 145. I still have the same 4 steps. I'm kind of going in autopilot mode a little bit there. I'm starting with my hypotheses. My null hypothesis is always going to be parameter, in this case I'm working with percentages, equals number, 33%. If you'll recall in the last problem, it started out just like this as well, so it seems like nothing's really changed. Except for this symbol here, I'm not testing for less, I'm not testing for more, I'm testing for different. Different actually means both less or more. So when it comes time to draw this picture, when I'm calculating this p-value, I'm going to notice a tail for less. This is always going to have a negative z-score here. And a tail for more. This will always be some positive z-score. So I'm going to have kind of a plus or minus situation. Step 2, my model. Percentage, so I'm using my percentage model. I'm going to be looking at sample p hats. That's just the name. N tells me that when I draw the picture, it's going to look like a bell curve. It did. P is my claim. P is 33%. If P is 33, then Q is 67. If you're having a little bit of deja vu, this is literally the same setup that we just had in that last problem. Very little changes. I'm still going to have a center of 33. I'm still going to have a standard deviation of 0.021. In fact, my assumptions will not change either, so I'm going to refrain from checking them this time, but they remain random, independent, and a large n. My third step, p-value. The p-value is the likelihood, so I'm looking at the likelihood of something, the probability of something, of my sample data. Well, my sample data is still this 145 out of 500. My sample success rate is still 29%. So on my curve, the center of the model is 33, and my sample is still showing up here at 29. Or more extreme. Or more extreme in this case means does not equal. And that symbol is coming from the alternative hypothesis. Whatever amount that it's less than 29, I'm thinking that's just as likely that it's bigger than whatever this mystery value is over here. Now the picture is actually symmetric. So if I notice that this is 4% away, this is 29, I could actually figure out that this would be 37 up here, as the same distance away. I'm not even worried about that though. I'm just going to go through the motions and find the z-score. So my process in these two-tailed tests is I'm going to calculate the z-score. I take my value, 29, minus the center, 33, and I divide this by the standard deviation. I still get the same z-score of negative 1.90. This is just my note. This is exclusively for two-tailed tests. So for two-tailed tests, you should look up the negative z-score. Because on my picture, I have two z-scores. I have a negative 1.90, and the other z-score on this other side would end up being a positive 1.90. So I can either take the size of this left tail and multiply it by 2, or the right tail and multiply it by 2. The nice thing about the left side is the table is the left side. So if I want the size of both tails, I can just do 2 times the table value if I look up that negative z-score. So in this case, my p-value is going to be equal to 2. I have 2 tails. My table value, I'm going to look negative 1.90 up in my table. When I do that, I get 0.0287. When I do 2 times this, I get 0.05. I'm going to type it into a calculator. 0.74. And if you're like me, I got to the 5 and I already got excited there because I kind of knew what the conclusion was going to be, because it's like, oh my gosh, this is actually larger than my alpha level, where on the last problem it was smaller. So this time my p-value is greater than my significance level of 5%. So this is a statistically not significant result. It is not smaller. So since it's larger than 5%, I fail to reject the null hypothesis. So I do not have evidence that the proportion of SUVs is different than 33%. So if you're wondering, well, hold up. In this last problem, we tested if it was less than 33% and we had evidence that it was less. Why do I not have evidence of the difference if I had evidence that it was less? That feels like I'm getting different results. The reason for that is you're not just testing for less, you're also testing for the potential larger. So you are really testing for two things. As a result, it takes twice as much evidence to say something is different and half as much evidence to say that something is either less or more. In a lot of ways, testing for a difference is the most conservative or risk-averse way to see if something has changed. This is one of the reasons why testing for a difference tends to be a more common type of hypothesis test. It's just more careful going through the process. If you're looking through the rest of the packet, you'll notice that there are just a ton of problems to go through here. I would encourage you to go through them. They are all the same setup. They are all this four-step process of hypotheses, model, calculate your p-value, and determine your conclusion. That's all for this lesson. Continue to practice. Ask me questions as things come up. I'm happy to help.